Okay, this is lecture 37. We're going to be talking about the limiting distribution for the birth and death processes. So remember, this is what we had last time with the birth and death processes. Basically, we had the schematic where you can only move up or down. You move down with a rate of mu I, and you move up with a rate of lambda I. So remember last time we talked about the infinitesimal generator matrix Q here. We had this form. So if we're looking for the limiting distribution pi, what we're looking for is the vector pi 0, pi 1, all the way up, such that q pi is equal to 0, and also the sum of all of our states is equal to 1, where obviously the pi I has to be positive, because here we're looking at the limiting distribution, so they have to sum to 1, right? So, and here we have this theorem for how to find the limiting distribution, what the limiting distribution actually is. So for some birth-death process, in which it's a finite birth-death process with finite state space 0 to n, then we have a unique positive stationary distribution if and only if our mu i's are positive and our lambda I minus 1's are positive for all I going from 1 to n. So in the way that we actually find our pi I is it has this form. Our limited distribution has the form Ri divided by the sum of all of our R's, where I'm going to tell you right now what these R's are. So R0 is defined to be 1. Then for every other I going from 1 all the way up to n, Ri is defined as the, if we multiply all of our birth rates all the way up to I minus 1, and we multiply all of our death rates starting at our mu1 all the way up to our ith one. So let's walk through here a proof of how you actually find this. So remember, this is our q and this is our pi. We're looking for pi. So we want q pi equals 0. Well, q pi equals 0, if we multiply this together, we're going to have negative lambda 0 times pi 0 plus mu 1 times pi 1 has to equal 0. Just doing matrix multiplication. Similarly, for the second line, we're going to have lambda 0 pi 0 plus this term here times pi 1 plus mu 2 times pi 2. This gives us the second line here, and we can keep on going. So what we can do is we can look at each equation, and we can do this recursively. So here, if we look at this equation here, and we're looking at solving for pi 1, so we're trying to get everything in terms of pi 0, then what we get is we have pi 1 is simply equal to lambda 0 over mu 1 times pi 0. So eventually what we're going to do is we're going to be able to get rid of pi 0, but right now we're going to put everything in terms of pi 0. So this was our second equation that we had. So again, now we're going to solve for pi 2. We wanted to set pi 2 equal to something, and we want to have only pi 0 in the right-hand side. So the way that we can do this is, here's our equation, so just put this mu 2 pi 2 on one side, everything else on the other side. And then for pi 1, substitute in what we already know. We can do a little rearranging here, take out our pi 0. So we have this term minus our lambda 0. But notice here what this is lambda 1 over mu 1. Here the mu's would cancel out, so you just have lambda 0 minus lambda 0. So what we basically get is we have mu 2 pi 2 has this formation, so we can divide by the mu 2, and we get something that looks really like our form of our r's that we had, except for we have this pi 0 here. So keep on going, and we can do this by induction. So once we have our pi's, in terms of our pi 0, let's apply the fact that the sum of all the pi's have to be equal to 1. So we can separate out our pi 0 from everything else. So we're going to get pi 0 in terms of all the other ones. So here we separate pi 0 from everything else. So we can say this is pi 0 times 1 plus the sum now starting at 1, not 0, all the way up to n of our pi I divided by pi 0. So what this tells us is that we can have a form for pi 0. So pi 0 is just 1 over 1 plus this thing, which is 1 over, here I'm going to substitute in what I had for pi I. Remember, pi I was written all in terms of pi 0, so this was our pi I. This is our pi 0. Pi 0 cancels out, and we just have this, which is our our I's, some of our RKs. So let's do an example. We're going to think about being in a barbershop in which there are two barbers, so more of the old-timey barbershops, and each has its barber chair. So we're going to assume that at most 5 customers can be there, so 2 can be in service and 3 waiting, so you only basically have 3 chairs in the waiting room. And you're going to assume that there's a potential for customers to arrive according to a process process at this rate lambda equals 6 per hour. And customers arriving when it's full, they leave, they're lost, you don't get them back. So we assume that the duration of each haircut is an independent exponential random variable with mean of 15 minutes. So basically, we're going to use this to actually figure out our rates. And customers come on a first come, first served basis. So this is kind of a schematic. Maybe we could only have 5, so we can have 2 in service and 3 waiting, or we could have no customers in there, right? So what are our lambda I and mu I given this schematic? Well, if we look at this, we're told that the customers arrive at a rate of lambda 6, a rate of 6 per hour. So each of our lambdas here are if somebody arrives, right? So each of our lambdas will be lambda I equals 6 for I going from, actually this should be, so I going from 0 to 4. Okay, now we look at our mu's. We have to think about this differently. So mu's are the rate at which a customer gets done. So basically the rate at which a customer leaves. So if we only have one barber working, so here, what's the rate at which we go from 1 to 0? Well, this barber gets done at an average rate of 1 per 15 minutes, or basically 4 per hour. So mu1 is going to be just 4. But now when you have 2 or more customers, both barbers are working. So the rate at which one person's going to leave is going to be the minimum between the 2 barbers. So which barber gets done first? Remember, the minimum of 2 exponential variables is also an exponential variables, but with parameter mu plus mu, or 2 mu. So this means that there's going to have a mean of 2 over 15 minutes, or 8. So mu2 all the way up to mu5 will be 8. So now what's the long run proportion of time that customers are in service and customers are waiting? And let's answer also the question is, what is the long run proportion of time each barber is busy? So we also have this note that 2 barbers are each busy half of the time when only 1 barber is busy. So to answer these questions, we need our limiting distribution. So remember what form we had for our limiting distribution. We had this formula here for our limiting distribution, formula here for the limiting distribution. So our R0 is equal to 1. Let's calculate the rest of our R's. So our R1 is lambda 0 over mu1. So remember, lambda 0 and all of our lambdas are 6. Here our death rate mu1 is just 4, so we get 3/2. And then we do this formula. We have lambda 0 times lambda 1 over mu1 times mu2. Just doing this, we get 9/8. We can do this for all of them, and we get the R's that we need to find our limiting distribution. We sum them all up, and so then we can calculate our pi. Remember, our pi's are, our pi 0 would be our R0 divided by the entire sum. Pi 1 is R1 divided by the entire sum, etc., etc. So we get our limiting distribution. So what's the long run proportion of time that 2 customers are in service and 2 customers are waiting? So 2 customers in service and 2 customers waiting basically mean we have 4 customers total. So we're looking for pi 4, which is 0.11. So what's the long run proportion of time each barber is busy? So, and again, we assume that when there's only 1 barber busy, so we're in that state 1, that each barber is busy half the time. So what we're really looking for is summing up the barbers are busy whenever you have half the time when you have 1 customer. 2, 3, 4, 5 customers, both barbers are busy. The other way you can think about this is just subtracting off the things that you're not interested in. So this is going to be 1 minus the half the time they're not busy, and then the time they have no customers. So in this case, the long run proportion of time each barber is going to be busy is about 0.7. And this is actually what's called a queuing model, which is famous. We're not going to be able to get into too much at all about queuing models. This is pretty much our example of a queuing model. But the queuing model is a Markov arrival process, MM23, where the 2 stands for 2 servers, the 2 barbers that we have, and 3 stands for how much of the waiting space we have. So the next time we're going to look at the Gillespie algorithm, which is going to help us to simulate what some of our continuous time Markov chains look like and how we would actually use this in real type of modeling problems.